is this topic called projectile motion. It's the idea that you're going to launch an object at an angle, and when you do, it's going to look like this. Okay, and so we're going to try to analyze the motion of this object as it travels through the air. All right, let's begin. So I'm going to fire this. So one of the things I want you to take a look at is if we take a look at the cannon, this cannon has the ball already, the cannonball inside, but the thing that pops up is this green line there. Okay, that represents the y velocity, and we have this green line at the bottom along the x-axis that represents the x velocity. So I'm going to push it forward frame by frame so you can see the vectors on your screen moving with the cannonball. Now, one of the things I want to point out is focus on the y vector. Okay, so this is the y velocity. As the object reaches the peak, okay, we can see that the y velocity, it went from a pretty big y velocity and it approaches it's shrinking. And so we can say that it's shrinking and eventually it will reach a y velocity of 0. Now, the y velocity is 0, I think, yeah, there we go. We set it so that it's at the peak. But after that, okay, what's going to happen with the y velocity is that the y velocity vector will actually swap signs. So it's going to go from a positive y velocity to a negative y velocity. And the reason why it goes to a positive to a negative is simply because the object is either rising or it's, in this case, it's falling. And notice what happens. As the object is falling, that y velocity vector is increasing. And we'll take a look at the graphical analysis that tells us that. All right? Okay. The other thing I want you to focus on is when we fire this again, take a look at the x vectors. Okay, so when we take a look at the x vectors, let's do this here, the horizontal motion, notice that the size or the magnitude of that x velocity, it does not change. We can see that the y velocity is changing, but the x velocity does not. And for this course, right, in the absence of air resistance, this is actually one of the fundamental, little memorization points that you have to keep in mind. The x velocity does not change. So I'm going to say that one more time, but I'm going to replace the words strategically. So a change in velocity, that is the acceleration. So if I'm saying the x velocity doesn't change, what that tells us is that there is no horizontal acceleration. But we clearly saw that the y velocity does change. So the question now becomes, what is changing the y velocity? Well, we know that when an object is in the air, there is an acceleration that acts on it in the vertical axis, and that's the acceleration due to gravity. And that's where we will begin our notes. Vertical axes. So I'm going to start off by drawing the position time, velocity time, and the acceleration time graphs. So the first one will be position versus time. The second one will be velocity versus time. And at the very end, I'll include the acceleration versus time. So there's a couple of things that we know. In terms of the position time graph, sometimes you might see me write it as x for position, and sometimes on problems you'll see it written as y for the vertical position. Okay, but both y and x just denotes the position of the object. So this is what we know. We know that the object launched with an initial vertical velocity. And so the slope for position versus time graph gives us the velocity. So I'm going to start off with a vertical slope there. We know that as it travels, that vertical component, that vertical vector shrinks until it reaches a size of 0. So this part right here, I'm just going to do dotted lines in between so you can see what I'm referencing. This part right here, this is the rise, okay, the vertical rise of the motion. All right, and after that, after it reaches the peak, oh, right there, this is important, this is the peak. Okay, so if I'm going to leave you with a couple of things to memorize, right? So the things that keeps on popping up. At the peak, the velocity at the peak will always be 0 meters per second. So what that means is that the object is rising, 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 rising until it can't rise anymore, and then it starts to fall. All right. Now I'll do the latter half in a different color. So after the peak, okay, the velocity is 0, but then it starts to fall. Okay, so we're going to start off with no velocity, and then we're going to have it go downwards with a negative velocity, like so, and I'm going to finish the curve in between with dotted lines, right? I'm just using the dotted lines to show you the motion of the line there. All right, so we can see here that the peak, the velocity is 0. So let's say Vy will be 0. And this is going to be true for all the cases, right? At the peak, the velocity is 0. Now, we've done many problems like this where we are looking and analyzing the motion of these graphs. And so if you have a position versus time graph that's curved like this, what that means is that there is an acceleration that's involved. Okay? And the acceleration that's involved here is going to be the acceleration due to gravity. Now, here we're going to say A of G is going to be, the official number is negative 9.8 meters per second squared, but for the sake of the math in our class, I will always round that up to be negative 10. Now here's the important thing, that negative is important for the formulas, but the meaning of that negative, in my opinion, is more important. This tells us that gravity, or the acceleration of the gravity, will always be pulling us downwards. We always accelerate downwards. Or a different way of saying it is that our velocity always changes by a negative value. Okay, so let's translate this position time graph to this velocity time graph. So let's think to ourselves, we have a constant velocity, or excuse me, a constant acceleration. Therefore, we have a constant slope, right? So the slope for a velocity time graph is going to be acceleration. And in this case, because we're looking at the y-axis, this is going to be negative 10. In the beginning, we had a positive velocity, but then as this positive velocity, or as the object was moving up, this positive velocity eventually reaches 0. So I'm just going to use dotted lines to fill in the middle. So we start off fast, and then eventually we come to rest. Now, the important idea is the object doesn't like freeze midair, right? It just freezes in the up and down axis, not side to side. It's still moving side to side. All right, and here's the important thing here. This slope is going to be negative 10. All right, now after we reach the peak, you know what? I think that's important enough for me to put that down. That point right there is the peak. After we reach the peak, the object starts to fall with a negative velocity. It starts off slow, but then we speed up. Okay? All right. And so you can see this is almost like a mirror image of itself. So the velocity / the time that it takes to rise up is the same amount of time that it takes to fall down. And in physics, we call that symmetry. All right. Now, the other important thing here is that the slope is still the same. It's going to be negative 10 meters per second squared. All right. So if we were to go from this position time graph to this velocity time graph, the final graph, we haven't seen a acceleration time graph before, but we know that the acceleration is a constant negative 10. Therefore, it would look like this. This is going to be the negative 10. Okay, now what about the horizontal stuff? So if we were taking a look at the horizontal motion, or the x-axis, okay, this is the horizontal. Okay, in that simulation I showed you, the horizontal vector, it doesn't change. So what that will look like in terms of your position time graph, okay? So remind yourself, the slope represents the velocity, and for the horizontal component, that horizontal component was constant, all right? So here, what we're going to be looking at is we started off at position 0, okay, and the object moved to the right. So it's going to move to the right like this. And so it's important that you see here, compared to the graph from before, right, where here we have a curved position time graph, which shows us there's acceleration. Here, there is no curve. It's a straight line, which means that our velocity is constant. And this is a big idea for this part of the unit. All right, so with that being said, if we were to go from a position time to a velocity time graph, okay, our velocity is constant. I'm just going to make up a velocity value. So it's a constant horizontal velocity. Okay. Now, as a reminder, the slope for a velocity time graph gives us acceleration. And if we take a look here, if the line is flat, the slope is going to be 0. All right. And this will be true for all of the projectile motion problems that we do. So with that in mind, let's come up with our acceleration time graph. So acceleration time graph, our acceleration is 0. and therefore it should be just along this axis here. So what we're seeing here are two very distinct graphs. The top one will be for the vertical motion, okay, where there is acceleration, and the bottom one is for the horizontal motion, where there is not any acceleration. All right, so this brings us to the tool that I think is the most helpful tool for all of kinematics and for Unit 1 is the kinematics table. So the way that I do the kinematics table, because we have two of them, either you could write the kinematics table twice, or I'm just going to do it like this: VO, VF, A, and T. I do X and Y. Right? I just like to create just one giant table where we can write all of the important information. So let's write a couple of the important information. Let's do the y-axis first. So if we are released from the ground or the floor, okay, our usual initial y position is going to be 0. Now, they will be tricky on the AP exam, and they won't always say you release the object from the ground or you don't shoot the object from the ground. It's shot from an initial height. Okay, so look out for that. So I'm going to write the word height. Okay, look for your starting height. XF, if it lands on the floor, once again, floor represents 0, so I should write that there. 0 is usually the floor. Okay, but it's really dependent on what the problem gives you. VO. All right, so VO is something that you have to find. So I'm going to write the word find there, and I'm going to show you how to find VO over here in a little bit. Okay, VF is something you usually have to find. All right, but here's the important part. You usually have to find the time first. Either that or they have to tell you the time to analyze. Right? So VOY and VFY are the ones that you have to find. And I'm going to do this in a different color because it's almost a constant. The acceleration for us will be G, aka negative 10 meters per second squared. All right? And the time is something that you're going to find based off the kinematic equations. Right? And here, I'm going to just leave you a note in red. I'm going to say about like 95%. Right? If you ask me, how did you come up with that number? I don't know. I didn't do any calculations. But nearly every single problem that you're going to do, the time for travel comes from the y-axis. Okay? So it's usually a y-axis problem. Now, there will be some times when you're doing the kinematic formulas and the problems where you just don't have enough information in the y-axis to give you the time. And if that's the case, you just have to use the x-axis information. All right, let's do the x-axis stuff. So XO is usually your starting position. If they don't tell you the starting position, it's almost always 0. XF. So sometimes in the problems, they ask you to find the range. Okay, so range is just code for XF. So I'm going to write that there. VO and VF. Here's the important part. We just saw with the vectors that these two are the same. Okay, so if you find VO, that is VF. The idea behind that is you have 0 acceleration. So I'm going to do that in a different color because this pops up every single time. Okay, your acceleration in the x-axis is almost always going to be 0 meters per second squared, unless you're doing a air resistance problem, and we won't tackle that until way later in this course. All right, and then of course time is time. Now here's the important part: the time of flight for the y-axis is the same time of flight for the x-axis. Right? Time doesn't care about the dimension. So if I were to highlight a couple of things for you to just memorize down, I would say range is XF. Okay, VO, VF is the same, and this right here, this idea of the acceleration being 0, and G. Okay, so those are the things when you create the table will almost always be the same ideas. All right, so I've been hinting at the idea of how to find VO and how to find VF. So let's do that over here. So let's do a quick sketch of a scenario that we just saw. This is my floor. This is the object, and this object launched like so. All right, so what I'm going to draw first is the actual velocity. So the actual velocity, I'll do this in black. will be this vector right here. So this is VO, okay? So this angled velocity can be broken down into its x and y components. This will be called VOX, and this right here will be called VOY. Now, sometimes you might see me write VOY over here, and in fact, in the simulation, that's where we saw it. But the reason why I put VOY over on the right-hand side there is so that we can see this right triangle. And that right triangle is critical for our problem-solving process. So essentially, what we have here is a right triangle, and this is just describing the initial launch. Keep in mind that VOY shrinks as it reaches the peak until it reaches 0, and then expands again, but in the negative direction. But that VOX, it never changes. All right, so I'm going to redraw that triangle down below without the path so that we can see how to do this math a little bit easier. So this is VO, this is VO but the Y component, and this is VO but the X component. Arrowheads, arrowheads, arrowheads. Okay, don't forget those. And the angle will be right there. Okay, so this is where the trigonometry part of the course comes in. So in almost all of the problems, they will give you VOY. I'm going to write the word here. It's usually given, unless the whole purpose of the problem is to find VO. Okay, so VOY or VO is almost always given. It is up to you to fill out that kinematics table. You have to break down VO into its two components, its horizontal component and its vertical component, so that we can fill out the rest of that table. So if you're given this angle theta, okay, so that's the angle that the object is launched, you need to be able to find VOY. All right, VO is your hypotenuse, okay? Your angle's right there, and here's your 90-degree angle. So if we were to use the idea of SOHCAHTOA, right, according to this angle theta, VOY, this is our adjacent side. According to this angle theta, VOX, VOY, that is our opposite side, and VOX is our adjacent side, and this is our hypotenuse. So I'm going to do the trig functions of sine of theta is equal to opposite over the hypotenuse. So if the question, or if you're trying to find VOY, I can rewrite this like so. Sine of theta is equal to the opposite side, which is VOY, over the hypotenuse, which is just VO. Okay, so I'm going to try to reiterate this again. Just put a little star there because it won't always be the case. But VO is usually given, okay, within the problem itself, and VOY is you gotta solve. Okay, you gotta find it. Find for the table, because we want to fill in as much of that table as possible in order to actually solve the problems. Okay, so for those of you with savvy eyes, you're like, okay, I think I understand what you're trying to get at, Mr. Lee. If we're trying to solve for VOY, and we know that sine theta is equal to VOY over VO, VOY just becomes, VOY just becomes VO, which is the actual velocity of the object, times sine of theta. Okay, so I want to point out this idea here, where if we were to break this this formula down, okay, another way to think about it is that VO is just the initial velocity, which is right there, and this sine theta right there is describing this vertical part, or the y component of it. Okay, so if you can't remember your trig functions, this is almost like a shortcut way of trying to come about it. Alrighty? All right, let's do the same, but for VOX, if the opposite side of this theta is going to be using sine, the adjacent side will be using cosine. Now, don't try to memorize it that way. It won't always be the case, but cosine of theta is adjacent over hypotenuse. Okay, if I were to use my vectors, adjacent will be VOX, and our hypotenuse is VO. So if I were to algebraically reorient this, to find Vox, it will be equal to VO times cosine of theta. And once again, you need to find for the table, okay? And VO is usually given. Okay, so I'm going to just show you one more time what this formula tells us. We can see here, this is VO, that's the actual velocity of the object. This is the actual velocity of the object. And so what cosine of theta is telling us is that we are multiplying the actual velocity of the object, but by multiplying by cosine of theta, we only get the horizontal component. It's actually a little math with ratios there. All right, so that's how you find VOY, and that's how you find VOX. To find VFY, you have to use the rest of the kinematics table, or the problem might be like, oh, hey, what about at the peak? Okay, so if you are ever analyzing the object at the peak, just keep in mind, right? This is one of those things you just got to memorize. Excuse me, I wrote VOY, but it should be just VY. Vy at the peak is going to be 0. So what that tells us is that at the peak, we're not going up and down, but we are still moving forward. All right. Now, there will be situations where you're not given VO, but there are ways for you to find VOX and VOY. So if you're not given VO, but you are somehow able to find VOX, and you're somehow able to find VOY. So this is something that I've been asking you on the daily checks, right? The question is, how do you combine X and Y vectors? And this is the big moment. This is the reason why I've been asking you. The only way you can combine your X and your Y vectors is with the Pythagorean theorem. So the hypotenuse, which is VO, okay, in order to find VO, you have to use the Pythagorean theorem, and so it would be VOX squared plus VOY squared, and that will give you VO squared, okay? And that is the only way you can find VO, aka the hypotenuse, if you're given just a X component and a Y component. All right, in the next set of videos, I go over a couple of practice problems so you can see all of this in action. The last thing I want to remind you is because we are now dealing with angles, okay, so I'm going to go back here. So in your notes, go back to this part here. I'm going to do this in red. Big stars must be in degree mode. Okay, I'll try to remind you in class to switch to degree mode. I'll try to remind you to switch your decimals to degree mode because in calculus, you'll start to use radian mode, and you got to make sure that your numbers, or excuse me, your calculators are in the appropriate mode so that you get the correct answer. All right, see you later. Bye-bye.